Welcome, guys. My name is Vincent Nando. I lecture at University of Nairobi. In this presentation, we are going to discuss about derivation of the general error formula in a function. So the first step, we are going to describe how to get or calculate or approximate the errors in a function of a single variable, and then thereafter we'll be able to derive the error in a function of several variables. So let's start by defining error in a function of a single variable. So to derive the formula, so the first thing, Taylor series. So Taylor series of a function about a point x naught is given by f of x is approximated by f of a plus x minus a, first derivative of x at a plus x minus a squared over 2 factorial f's double prime at a plus other terms up to x minus a raised power n divided by n factorial, then nth derivative at a, then plus remainder term. So we are going to, this is the Taylor series of a function f of x at x or about the point x equals to a. So let's call this Taylor series, call it 1. So let's approximate a value a of x by a. So this is what I mean, that the error in this value a is given by the true value a minus the approximate value of a. So replace x equals to by a in 1. So that will give us f at by a, which is the approximate value of a, is given by f of a plus by a minus a, part derivative at a plus by a minus a raised power 2 divided by 2 factorial, and then second derivative at a plus other terms of the same pattern. Now, since a by a minus by a equals to error in a is assumed to be a very small value, in magnitude, then we can ignore or simply neglect higher terms, higher order terms in this difference of error in a. And therefore, remember, this can be written as f by a. So remember, this approximately equals to, so approximately equals to f of a. And then I can write this one as minus a minus by a f prime at a minus, say plus minus a minus bar a squared over 2 factorial second derivative at a plus other several terms of the same kind. So with this assumption that this difference is very, very small, then from this point here, from this point, all these values will be 0 because this difference is very, very small. So therefore, we have f of bar a is approximately equals to f of a minus bar a f prime at a. So then we can rearrange this one as, or you can just write it as f bar a is approximately equals to f of a. And then this define the error in a. So minus error in a, f prime at a. So we make this one the subject and we have error in a, f prime at a is approximately equals to f of a minus f at bar a. Now the value f of a is the correct value of the function at a, f of bar a is the approximate value of the function at a. So therefore, this difference defines the error in the function at point a. So this can just be written as error in a times derivative of the function is approximately equals to the error in the function at point a. So therefore, error in function of a single variable is simply given by, you find the error at that particular point and then multiplied by the value of the derivative of the function at that same point. So this is the error formula in a function of a single variable. And then case 2, general error formula. So the first case, we derive the error for a function of a single variable. But now let's see if we have a function of several variables, how we define the error. So we start by saying, let u be a function of several variables x1, x2, x3, up to xn. So i.e., we can write u as u of x1, x2, x3, up to xn, or just the same thing as right saying f of x1, x2, x3, up to xn. So this means that u is a function of several variables x1, x2, x3, up to xn. So call this one question 1. Now, next thing we say, let epsilon x1, epsilon x2, epsilon x3, up to epsilon xn epsilon xn be error magnitudes in x1, x2, x3, up to xn respectively. So this is what we have. Then we can denote the error in the function by just saying error in U. So that's how we can write it. So therefore, we can write so this is what we have. That when you say U plus error in U, then it will be simply a function of x1 plus error in x1, comma, x2 plus error in x2, x3 plus error in x3, up to xn plus error in xn. So when you say the function U plus its error, then it's a function of the variables x1 up to xn plus their corresponding error magnitudes. So let's call this one equation 2. Now, we then expand the right-hand side of 2 using Taylor series. For a function of several variables. i.e., will have U plus error in U is given by now. When you expand this one in Taylor series of function of several variables, we'll have f of x1, comma x2, comma x3 up to xn, and then plus error in x1 partial f partial x1 plus error in x2 partial f partial x2 plus error in x3 partial f partial x3 plus error in xn partial f partial xn plus other terms, other higher order terms in error of xi. So where I is 1 to n. So remember here means just to make things clear, this one means higher order terms in these error terms. Higher order terms, higher order terms in errors. And then I is from 1, 2, 3, up to n. So this was just by the way. So let's call this one equation 3. Now, since these error magnitudes are assumed to be very, very small numbers, then all the higher order terms in errors will be assumed to be 0. Then that's a very key thing that you need to remember when we are doing this derivation. So since the error magnitudes epsilon subscript xi are assumed to be very small, then we can neglect these higher order terms in these errors. So therefore, Therefore, 3 just becomes, now let me just write, u plus error in u is equals to, and then, so remember from here we say that u equals to u of x1, x2, x3 up to xn, which is the same as a function of x1, x2, x3, x up to xn. So where there's f of x1 up to xn, you can put u of x1 up to xn, or you can put just u. So therefore, this, I can just write this one as just u from 1. So it'll be u, and then plus, then this term we just error in x1 of partial u partial x1, because f is the same as just u. So error in x1 partial u partial x1 plus error in x2 partial u partial x2 plus error in x3 partial u partial x3 plus up to error in xn partial u partial xn. So remember we said that higher order terms in error, these are 0, so that's why I'm just talking at this point here. So and then what's making us write this one, remember that f of x1, x2, x3 up to xn is the same thing as u of x1, x2, x3 up to xn, which is the same thing as just saying u or just saying f. So that's why from 3 I have this. So call this one 4. Let's call this one equation 4. Now from this equation 4, it should be clear to us that this u and this u cancels out. So therefore, error in u, which is the error in the function, is error in x1 partial u partial x1 plus error in x2 partial u partial x2 plus error in x3 partial u partial x3 plus other terms up to error in xn partial u partial xn. So this is the error in the function u. So therefore, this formula here, this is the error. This is the error in u, which is the function of several variables x1, x2 up to xn. One thing to note, few things to note here, that sometimes the errors in xi's can be negative. So to define the maximum error, then we take the sum of absolute values of each term. So let's call this one, say, called equation 6. Each term in 6, therefore, we say error in u maximum is actually less than or equals to error in x1 partial u partial x1 magnitude plus magnitude of error in x2 partial u partial x2 plus magnitude of error in x3 partial u partial x3 plus up to error in xn partial u partial xn. So generally, this is what you need to define whenever, this is how you need to define the error in the function whenever after carrying out the partial derivatives, some of the terms are negative. So the thing that ignore the negative signs and then they just get the values. So call this one 7. And then note number 2, the relative error in U is given by relative error in U equals to error in U divided by actual value of U, which will be given by 1 over U into error in x1 partial U partial x1 plus error in x2 partial U partial x2 plus up to error in xn partial U partial xn. So which can just be simplified to error in U is error in x1 over U partial U partial x1 plus error in x2 over U partial x2 plus up to error in xn over U and then partial U partial xn. So this is what we have. So this is the formula for finding the relative error in U, which is a function of several variables. And just as we have been given the note in 1, in case any of the derivatives is negative, then check its absolute value. So this is what I mean, that a relative error in U will be given by absolute value of this term, error in x1 over U partial x1 plus absolute value of error in x2 over U partial x2 plus up to error in xn over U partial xn. So this getting the sum of the absolute values of each term just eliminate the case of they're having the negative values in any of the terms. So that's how we get the relative error. And then if you have to find the percentage error in U, then just define the relative error in U and then multiply by 100%. So in the next video presentation, we'll be giving examples on how to find errors in functions of both single variable and several variables using these two, this formula that you have derived in this presentation. So thank you.